And today I'll be expanding a little bit on magnetic structures. So what we'll talk about today is how we can define a magnetic structure using propagation vectors in particular. Then we'll see how we can go from a neutron diffraction experiment to solving our magnetic structure. And we will briefly look at cubic systems and some problems that may arise there. We'll see how we could solve these problems with the external perturbations, focusing on magnetic fields. And finally, we will briefly talk about polarization analysis. So it's useful to think about magnetic structures in relation to crystallographic ones. And we all know that a crystallographic structure is a long-range ordering of atoms, and in the same way, a magnetic structure can be described as a long-range ordering of magnetic moments. And these are some very simple magnetic structures that many of you may already be familiar with. The first is a ferromagnet, so all our spins are pointing parallel to each other. Then we have three antiferromagnetic structures on a cubic lattice. So these different types of antiferromagnets only exist in cubic lattices. And when we say antiferromagnet, we basically think of spins pointing antiparallel to each other, but they can also be regarded as two interpenetrating ferromagnets whose magnetic moments exactly compensate one another. And you can see this, I think, most simply in this A-type structure. So these would be the black and the gray would be the two ferromagnetic structures. We can go a bit further and look at ferrimagnets. And in this case, the two different types of magnetic atoms have different sized moments. And so you'll have a net magnetic moment in this type of material. So to describe a magnetic structure, we basically need a magnetic motif. And this is much like the unit cell that you find in crystal structures. It describes the directions and the values of all magnetic moments. So if we just take a quick look at this Kagome lattice here, we have an 120-degree structure, and this green area gives us the magnetic motif. And by pure translation of this part of the structure, we can generate the whole magnetic lattice. And then the second thing that we need is what's called a propagation vector. And this gives us the periodicity of the magnetic structure with respect to the underlying crystal structure. So if we take a look at this transverse helix, what we have is a moment which rotates in the plane. And so if we start from the bottom moment, we have parallel planes of magnetic moments, where the propagation vector is perpendicular to these planes. And the distance between two planes where the moments are pointing in the same direction is given as L, and this is 1 over k, k being the component of the propagation vector in this direction. To understand this a little bit further, if we take a very simple chain of atoms which have a lattice spacing A, and we look in particular at a ferromagnetic structure, so all our spins are pointing parallel, and to recover the direction of our first moment, we only need to move a lattice spacing A. And we can say that our magnetic periodicity is equal to the nuclear periodicity, and our propagation vector is 0, 0, 0. A little bit more complicated, an antiferromagnetic structure. So we still have a lattice spacing A between our atoms, but now to recover the direction of the first moment, we need to move 2 lattice spacings. And so the magnetic periodicity is double that of the nuclear one. And our propagation vector, which is a reciprocal lattice vector, and so in this x direction, it is 1 over 2, a half, 0, 0. Now, we often think about a propagation vector of 0, 0, 0 being associated to ferromagnetic structures, but I just want to point out that it is possible to have antiferromagnetic structures with a propagation vector of 0. So in a case like this, where you have more than one magnetic atom in the unit cell. All of these structures are quite simple, and we can describe them with just one propagation vector, but there do exist some rare examples of more complicated multi-case structures. So we need more than one propagation vector to describe the structure, such as the one seen here. And in this case, the two propagation vectors that we need are 1, 0, 0 and 0, 1, 0. And a more mathematical way to describe the magnetic moment is through a Fourier expansion. So the moment distribution is a periodic function in space. And if we place a magnetic moment here on this arbitrary atom, the distance from an arbitrary origin is the distance from the origin to the unit cell. And this is what kind of comes into the periodicity of the whole magnetic lattice. And we also need the Fourier components of the magnetic moment, which are associated to a specific propagation vector. Now, experimentally, in the case of unpolarized neutrons, when we collect a diffraction pattern, the intensity of the peaks that we see is the sum of the square of the structure factors of the nuclear contributions and the magnetic contributions. And here we have denoted M perpendicular because, as Niels explained earlier, we only see the component of magnetization perpendicular to the Q vector. In the case where our propagation vector is 0, the magnetic and nuclear signals superimpose. And a good way to extract the pure magnetic intensity is by measuring above and below the magnetic transition temperature and doing a subtraction between the two diffraction patterns. And in the case where our propagation vector is not 0, the nuclear magnetic peaks appear at different positions in a diffraction pattern. So the way we go about this is we start with powder or single crystal neutron diffraction. Using powder diffraction, we can probe all of reciprocal space to unambiguously determine the propagation vector. Now, there are samples where people will start with single crystal diffraction. It depends on what kind of sample you have. But anyway, you can start with powder diffraction and then move on to single crystal neutron diffraction. And this way, if you already know your propagation vector, then you know where you're looking for your magnetic peaks in reciprocal space. So you collect your data, and if the magnetic phase transition is of second order with respect to the free energy, then you can do a symmetry analysis using group representation theory, which we'll discuss in a bit, or the magnetic space groups that Niels mentioned earlier. And then finally, you want to do a magnetic structure refinement to find out what your magnetic structure looks like. Experimentally, all you need is not all you need, but what you need is a neutron diffractometer, and we have plenty of those at the ILL. This is, of course, not a full list of the instrumentation available, but I just want to point out that depending on the type of sample you have, or perhaps the size of the magnetic moments that you have, you might need a different instrument if you need to apply some kind of magnetic field or pressure, or if you need to do polarization analysis. There are different instruments that you'd go for this type of thing. So we've collected our neutron diffraction data, and now we want to do some symmetry analysis on it. We won't go deep into group theory, but it's nice to understand how useful a tool it is to solve a magnetic structure. And the first thing we need is to determine our propagation vector, which we do by indexing the magnetic peaks in our diffraction pattern. And then from the crystallographic space group, we need to select the symmetry operators that leave this propagation vector invariant. And we take these symmetry operators and put them in a matrix, which is called the magnetic representation. And if we can decompose this, we can block diagonalize it like so. And from this, we extract what are called our irreducible representations. So the magnetic representation is just the direct sum of the irreducible representations multiplied by the number of times that they appear in the representation. Now, all this symmetry analysis, I mean, you can do this by hand, and people used to do it by hand, of course. But there also exist some very useful programs that will do this for you and make your life much easier. And what you need for these are your magnetic atom coordinates, your propagation vector, and your crystallographic space group. And you put these into programs such as Sarah, BASIREPS, MODI, or isotropy, and they give you your irreducible representations. So we have this magnetic representation. We said that it's the direct sum of many other irreducible representations. And Landau's theory for second order transitions tells us that the magnetic structure established at the phase transition corresponds to one irreducible representation that persists while all others cancel. This basically means that we only need one irrep to describe a magnetic structure. And in practice, to determine which one is best, well, we have to put them into some kind of a refinement program like FullProf or GSAS or YANA. And we just see what best fits our data. And so the irreducible representations are symmetry operators. They describe how the magnetic structure transforms under symmetry operations of the crystal space group. But to really define at the end of the day, what we want is the directions of our magnetic moments and the size of our magnetic moments. And for this, we must find the basis vectors corresponding to our irrep. Now, what are basis vectors? They are just the projection of our magnetic moment along the crystallographic axes. So if we have XYZ crystallographic axes, then we have, let's say, these three basis vectors along the three directions. And arbitrarily, if we put a magnetic moment, so it's this black arrow pointing in the ZX plane, then the basis vector that will define this, or the sum of the basis vectors that will define its direction, is a half 0, 0, 1 plus a half 1, 0, 0. And a half is the coefficient that helps us define the direction or the angle with respect to the crystallographic axis. So from this, we can see that the moment projection is actually a sum of multiple basis vectors multiplied by some mixing coefficient. And again, we can further expand our moment distribution to describe the whole magnetic structure. And you'll recall that a few slides ago, we did the same thing and we had these Fourier coefficients here. And in fact, the symmetry analysis relies on the fact that we can describe these Fourier coefficients as a linear combination of basis vectors. So you put these basis vectors in your refinement program, and what you refine are these mixing coefficients. And this is finally how you can solve your magnetic structure, and then you can visualize it and see what directions your moments point in. So now moving on a bit to cubic systems. As Niels already mentioned, the first evidence of antiferromagnetism was in fact found on manganese oxide, which is a cubic system. And you've already seen this diffraction pattern today. So what Shell and Smart did was they measured a diffraction pattern above the magnetic phase transition temperature of manganese oxide, which is at 120 Kelvin. So they measured at room temperature, and then they measured at 80 Kelvin. At room temperature, they could only see the peaks corresponding to the nuclear structure. And below the transition temperature, new peaks appeared, and these were the ones corresponding to the magnetic structure. And they indexed these magnetic peaks, and they found that the propagation vector is a half, half, half. And what this means is that the magnetic structure is a doubling of the crystal structure in all three directions. So you can imagine that the magnetic structure is 8 times the volume of the crystal structure unit cell. Now, this all seems quite simple, but there are a few issues that may arise in cubic systems, and one that was seen in manganese oxide. And for this, we have to introduce the concept of magnetic domains. Now, there exist 4 types of magnetic domains. There exists these 180-degree domains where one unit cell is just, well, the spins on the unit cell are just rotated by 180 degrees with respect to the first one, but the propagation vector is in the same direction. We can have orientation domains, or S domains as some people know them. We can have configuration domains, or K domains, and these are the ones which I'd like to focus on for manganese oxide. And in the case of configuration domains, by by rotating the spins of the if you imagine that these spins are sitting on the cube and we're just rotating the cube in a sense, the propagation vector also changes direction. And then the final type of magnetic domain that may arise in some samples are these chiral domains. And if you look closely at the top, you kind of have the spins rotating, let's say downwards, and in the bottom, they are rotating the other way. And it's known as like left-handedness and right-handedness of the chiral domains. But anyway, let's focus on the K domains. So let's take a bit of a closer look. If we have this structure over here, you can see that in the XY planes at the bottom, all of the spins are pointing in the same direction, but they are opposite to the ones at the top. So the propagation vector in this case is 0, 0, 1/2, because we would need to travel double the unit cell in the Z direction to recover this moment direction. And again, if you just imagine that the structure is just kind of rotated by 90 degrees, but now our propagation vector is 1/2, 0, 0, so in the X direction. And what happens is that when the system cools, so these two structures are degenerate, and when your system cools through the magnetic phase transition, there is no reason for it to pick one structure over the other. And some parts of your sample may order in one domain and some in another domain. But when this happens, you see it in your diffraction pattern as extra magnetic reflections. Now, there are cases, so we already spoke about multi-K structures in the beginning, and this just means that we need more than one propagation vector to describe the magnetic structure. So this magnetic structure over here is described by both of the propagation vectors that we had in our multi-domain structure. And this multi-K structure will also result in additional magnetic reflections in the diffraction pattern. And in fact, they will result in the same additional magnetic reflections that we had in the multi-domain case. Now it can get more complicated. You could have a triple K structure where you need the additional 0, 1/2, 0 propagation vector to describe the structure. But the point is that having a multi-domain structure with these two propagation vectors, or this double K magnetic structure, will result in the same additional magnetic reflections. And you would need some kind of external perturbation or polarization analysis to distinguish between them. So by external perturbation, you could use, for example, a magnetic field or uniaxial stress. And what this will do is that if you have a multi-domain structure, it will change the population of the two domains, and this will change the intensity of the peaks that you see in your diffraction pattern. But if you had a real multi-K structure, then the intensity of your peaks in your diffraction pattern should not change. So let's just consider the case where we apply a magnetic field. This is for the case of a ferromagnet, but the principle is the same. So here we have many domains of ferromagnetically aligned spins in zero field, and then we apply a field along the Z direction. And what happens is that all the domains align parallel to each other. And we can take advantage of this by applying the magnetic field parallel or perpendicular to the Q vector of the neutron beam. So in the zero field case, which is this picture up here, the intensity that we see is defined by this. So the square of the structure factor of the nuclear contribution plus 2/3 of the square of the structure factor of the magnetic contribution. And if we apply our magnetic field parallel to our Q vector, then we will only see the nuclear contribution. And we already know that we will only see magnetization perpendicular to our Q vector, so this just makes sense. And if instead we apply our magnetization perpendicular to the Q vector, now we will see the nuclear component and the magnetic component. And we can just subtract the top from the bottom to get our magnetic component. The other thing that we can do to distinguish between multi-K or multi-domain structures is use some kind of polarization analysis. And the most appropriate, I think, is spherical neutron polarimetry. Now, this has already been discussed in previous talks, so I'm not going to go too into it, but just a little reminder that when we do spherical neutron polarimetry, we measure the X, Y, and Z directions of the final polarization for the X, Y, and Z directions of our instant polarization. And the definition of the initial and final polarization can be written like this, with a polarization tensor, which is shown here. And in spherical neutron polarimetry, it is possible to measure these off-diagonal components. And these off-diagonal components are the ones that are related to rotations of the polarization due to domains. Now, some small disadvantages of spherical neutron polarimetry is that if there is a ferromagnetic component in our sample, then this can depolarize the beam. So usually people only measure antiferromagnetic or more complicated structures, but with a zero net magnetization. For ferromagnets, we could use half polarized neutron diffraction, where either the instant beam is polarized and the scattered beam has no polarization analysis, or the instant beam is not polarized, but there is final polarization analysis. And what is measured are the flipping ratios, which is shown, or the flipping ratio, sorry, which is shown here, where gamma is the structure factor of the magnetic component over the structure factor of the nuclear component. And we can get this from the crystal structure. And by Fourier transforming so we can easily figure out the structure factor of the magnetic component, and a Fourier transform of that gives three-dimensional spin density distributions. And usually what is measured using half polarized neutron diffraction are saturated ferromagnets, saturated ferromagnets, or if you put a paramagnet in an applied field, then you can induce some kind of long-range magnetic order that could be interesting to look at. And finally, the last polarization technique is uniaxial polarization analysis. And this has been presented on before, but just a little reminder that the initial polarization is set along an axis, and the final polarization is analyzed along this same direction. And we measure, well, what they measure are these four scattering cross sections, so either the non-spin flip or the spin flip ones. And what is most interesting in these experiments is to put the initial polarization parallel to the Q vector, so that the magnetic contribution is spin flip and the nuclear one is non-spin flip. And in this way, you can separate the nuclear and the magnetic cross sections. But in uniaxial polarization analysis, so only the diagonal components of the polarization matrix are measured. And so we lose any information about depolarization due to domains, which we would see in these off-diagonal components. So this was a lot of information, but basically what I told you today was that magnetic structures are described and solved in a very similar manner to crystal structures. Group theory sounds very hard, but representational analysis is an amazing tool to solve magnetic structures. We looked a bit at cubic systems and what kind of ambiguities may arise, and how it's necessary to apply some kind of external perturbation to clarify these ambiguities. But there are other systems where there might be multi-domain structures. For example, it's not just cubic systems. And then finally, we briefly looked at how the different types of polarization analysis may be appropriate for solving different types of magnetic structures. So I would like to thank Niels for many discussions about his presentations, Andrew Wiles for a very useful discussion on magnetism, my two supervisors. And I have included some references which I used for this presentation and have been very useful to learn about magnetic structures and diffraction. And thank you all for listening.